In a way it is good, in a way it is very bad. But when you get used to proving everything, it's going to be fun. Anyway, so we proved that this is true. We can now generalize the single choice lemma. Single choice lemma was if a set is non-empty, we can select something. Now we have to prove this finite choice. Thereafter, what you call axiom of choice. As I told you, that is the reason that we have this modern analysis. In fact, that's why we are here today. Because of this axiom of choice. It's very simple, but that's, I guess, the foundation of many things. Because even though you don't know integration, but the integration you know is Riemann integration. There's applications. I don't think you are taught what is the meaning of Riemann integrability, as well as what is the Riemann integral. In A level, all we need is we use that coca mark. In A level, you use this symbol, but you will learn. Let's see what finite choice is. Regardless of reading this, we can discuss it, but let's go through the book because that's what Dr. Prabhat knows. Let m greater than or equal to 1 be a natural number, and for each natural number I between 1 and n, let xi be a non-empty set. In single choice you had one non-empty set, here you have n non-empty sets xi. Then there exists an n tuple. N tuple means x1, x2 ordered, x1, x2 and so on up to xn, such that xi belongs to capital Xi for all I. In other words, if xi is non-empty, then the product set is also Cartesian product is also non-empty. That's what it says. In your way, you would say it goes without saying. But it's moving here. Proof. Let's say we induct on n. Another thing, by the way, here you are using induction for the things that somebody usually never use induction in this book. Because you use induction to do very difficult problems. Here for just little things, anything doesn't matter. We induct on n starting with the base case n equals 1. The claim is also vacuously true for n equals 0, but is not particularly interesting in that case. So nothing to do. No, when n is equal 1, the claim follows from lemma 3.1.6. I guess that is single choice lemma. So he is asking why, because you need to understand this, whether you say, we are identifying x1 and this x1, ordered x1. This one has just x, simple x, this one has simple x like this. The same thing. These are good for those who are interested in algebra for you, computer. So to you it is good. When n equals 1, try. Now suppose inductively that the claim is already been proven. Claim has already been proven for some n. Assume that it is true for some n. We will prove that it for n plus plus. That's what we usually do in induction. If it is true for n, then we prove it for n plus 1. We have already proved the case for n equals 1. Then by induction it follows for any n. So now we are assuming that the result is true for n. Now we want to prove it for n plus plus. Let x1, and so on, xn plus plus be a collection of non-empty sets. By induction hypothesis, we can find an n tuple. Because we are assuming the result is true for n. So you have now capital X1, capital X2 up to capital X and non-empty sets. Then by induction hypothesis, you have an n tuple, x1, comma, x2, and so on up to xn belongs to phi. In other words, x1, comma, capital X1 cross capital X2 cross capital Xn. Also, since xn plus plus is non-empty, by again lemma 3.16, we may find an object A such that A belongs to xn plus plus. If we thus define n plus plus tuple, first n coordinates yi is equal to xi, and n plus plus coordinate yi is equal to a, it is clear that simple yi belongs to capital Xi as well as for any n, thus closing the induction. I don't know if you have a better understanding than I do. I don't see any advantage of writing n plus plus now, because we have shown that n plus plus is nothing but n plus 1. I wonder why it is, it is written all over. I don't know. I didn't try to, understand it also, because I guess he likes to go with his, introduction, incrementation notation, I guess. It is intuitively plausible now, correct, no? Intuitively plausible that this lemma should be extended to allow for an infinite number of choices. It is of course plausible, we expect, but this cannot be done automatically. It requires an additional axiom, the axiom of choice, section 8.4. Again, in your case, you just did A level. You don't know anything about analysis. Before doing anything, he talks about all the other results. So this book is written for people, those who know analysis already. Axiom of choice. Why? What? You don't know anything about them. So I don't know why you should use this sort of thing, no? My glasses are. Are positioned. When you write parentheses x, comma, y, again parentheses, you really don't, of course you think you know it, but mathematically, we don't know what is the meaning of, open parentheses, x, comma, close y, then close parentheses. This is how we define it. This is the definition of x, comma, y. This is how we define x, comma, y, because in maths, everything is expressed by sets. Everything is expressed by sets. So now it is a good exercise, I guess, if x comma y is equal to x comma x1 comma y1. To prove this, these two are equal. Sometimes I give this thing for, I don't know, not for final exams, but tutorial problems in the Colombo University. Anyway, so let's proceed. Ordered interval A, these are show that the definition of equal to, again not interesting. These are matter of writing. Many questions like such will be sets, projection set, again writing. Show that Cartesian product is empty if and only if at least one of the xi is empty. Again, logical thing. This one suppose that I and j are two sets, and for all alpha in I let A alpha be a set, and for all B belongs to beta belongs to j, let beta be a set, so that this thing intersection is thing. Again, matter of writing. All of them are, though I say matter of writing, it's important that you write them. Otherwise, just by, that's true. By going like that, it won't help now. Anyway, you got the inductive proof of finite choice, no? It's simple, but anyway, we are, to us it is obvious thing. If I say it is non-empty, there is something. And if x1 up to xn, each set is non-empty, then you can choose x1, comma, x2, xn from the product, so that each xi belongs to capital Xi. But here, we are proving. Cardinality is a big difficult word, by the way, in maths. Difficult word, cardinality. He talked about ordinals also, no? Somewhere, I don't know why on earth he's, talking about it. Even though this is introduction using all the advanced things, as if the reader knows everything. Cartesian cardinality of sets. Is this correct? As an alternate. As an alternate formulation of the power set axiom for any set x and y, we use lemma 3.4.9 and the axiom of specification to construct the set of all subsets of x cross y, which obey the vertical line test. Vertical line test makes it a function, no? That there is anyway, let's proceed. You have vertical line tests are taught in A-level maths classes? Cardinality of sets. Cardinality. I myself have a hard time with cardinals. They are difficult. Over there you had cardinality problems, here you are teaching. That is the thing. So keep in mind, cardinal is there is Catholic religion. There is also cardinal. No?
So that's like a position.
Yeah, it is a position.
Yeah.
In the church.
Yeah. Like a father is giving the rank.
Okay, cardinality of sets. Let's see. Ordinals are very difficult. Very difficult in the sense they are not natural. Ordinals are not natural. I get tired because, but it's very important in maths. Cardinalities are more important than ordinals because you have to know cardinalities in order to do mathematics. It is not necessary for you to understand ordinals because it is. I myself don't understand it very well, but I have studied quite a lot of topology. Oh, ordinal spaces, amazing. In the previous chapter, we defined the natural numbers axiomatically. So that's why we did not these 5 piano axioms. Using that, we define natural numbers. It's a good job, I think. He assumes only we know the number 0 and then this increment operation plus plus. But in all the other things that I have seen, 0 and 1, both these numbers are taken for granted. He doesn't do it, instead of he writes plus plus thing. No? Assuming that they were equipped with the 0 and then increment operation. Others, it's 0 and 1. Now, for instance, after this book, I have written 2 books on foundations of mathematics. There, I have given the axioms of the real number system. Yeah, it is very clear. So I guess you should not read it now. Then you get confused. Here, something in my book, something else. So, but if you can understand both, it's good. Assuming that they were equal to the 0 and the increment operation, assuming 5 axioms of these numbers. Philosophically, this is quite different from one of our main conceptualizations of natural numbers, that of cardinality, or measuring how many elements there are in a set. So cardinality is about actually how many elements are there in a set. That's from where cardinality comes. Indeed, the piano axiom approach tests natural numbers more like ordinals than cardinals. I mean, it's very unfair, no? I mean, you don't know anything about ordinals. If you ask me about ordinals, actually I cannot explain also. To tell you the truth, I have a very passive knowledge. It's not concrete for me. But in analysis, for some examples, ordinals are important. The cardinals are 1, 2, 3. I used to count and how many there are in a set. The ordinals are first, second, third. And I used to order a sequence of objects. So anyway, there is a subtle difference between the two, especially when comparing infinite cardinals with infinite ordinals, but this is beyond the scope of this text. We paid a lot of attention to what a number came next after a given number n, which is an operation which is quite natural for ordinals, but less for cardinals, but did not. Ordinals is like first, second, third, that way. I mean, ordinal spaces, they are very, important in analysis and topology. So here, I don't want to read even this. We paid a lot of attention to what number came from, and its operation is quite natural for ordinals, but less so for cardinals, but did not address the issue of whether these numbers could be used to count sets. The purpose of this section is to address this issue by noting that the natural numbers can be used to count the cardinality of sets as long as the set is finite. If a set is finite, of course, since somebody asks you how many numbers, elements are there, you count, no? 1, 2, 3, 4, 5, 6, like that you can give the number. But if the set is infinite, then you cannot handle it. But it's the cardinal. There are, for instance, 1, 2, 3, 4, this set, he puts 0 also, no? This is infinite, no? And if you write real line, since you know it, real line, this is also infinite. Now you may have a question, is this infinity equal to this infinity? Like that you could have questions. And again there is another infinity. Now, power set of x. Power set of x means set of all subsets x, such that x is a subset of R. This is another infinite set. In fact, all these are different infinities. This infinity is the smallest infinity, and this one is the next, and this one is the next one. So usually people say infinitely many, then I guess they are assuming one of them without knowing that this one is bigger than this. Something you will learn in this course, I guess, number of elements. If you have read the book, he writes like, when it is finite, he writes like number of elements, this way, you know. So, you cannot write when it is infinite. But if you get, say, x is a subset of n, and then R. Number of elements in this set and number of elements in this set are equal. We may be proving it in the, I don't know. These are now subsets of not natural numbers. Yes, natural numbers, no, this is in subsets of natural numbers, and the number of elements in R, they are the same. It is something, I suppose, somewhere we will be proving. What is he saying? Now, we cannot go that far. Here, especially we are talking about the number of elements in a set when they are finite. We want to talk about the size. We want to say, for instance, this set has 3 elements. No? That's very true. the first thing is to work out when two sets have the same size. It seems clear that the sets 1, 2, 3, 4, 5, 6 have the same size, but that both have a different size from 8, 9. I mean, they are clear, no? One way to define this is to say that two sets have the same size if they have the same number of elements. We can talk like this when you have finite sets, but we have not yet defined what the number of elements in a set is. Besides, this runs into problems when a set is infinite. I told you the other day, I mean roughly, number of elements in R as well as number of elements in the 0, 1 are the same. We are going to prove it. I will prove it again. Now I can prove it, but I am not going to do it now. He is going up with this finite elements now. Try to see whether you can prove it. Number of same means what? I mean, how do you say, those who don't know how to count those days may say somebody is going to sell coconuts and somebody is going to sell oranges. Now, they can correspond, no? This one to this one, this one to this one, this one to this one. This is a one-to-one correspondence. So that's how, without knowing how to count, you can say this set has the same number of elements of this set. Same. When you have a one-to-one correspondence. That's how you prove that number of elements in the set of all real numbers as well as number of elements in the set of all real numbers between 0, 1 and are the same. Another little thing funny is, see, that's also funny, I mean R is so huge, 0, 1 is. Not only this, even if you take 0 to 0.1, number of elements here and number of elements here are the same. You can prove that you can match one-to-one correspondence. You agree, no, one-to-one correspondence is a good way to say that both sets have the same number of elements. That's how it is said. And funny thing is, suppose 0, 1, 2, 3, 4, this set, two. And this set, 2, 4, 6, 8, both these sets have the same number of elements. But this is a proper subset of this. But you can make a one-to-one correspondence. For one-to-one correspondence, anybody can agree whether you know maths or not. Even those who are doing arts degrees, I mean, they understand one-to-one correspondence. So like this, here I match this coconut to this orange, this coconut to this orange, this coconut to this orange. So coconuts are over, oranges are over, therefore both groups have the same number of elements. So here at the very beginning, that boy may not be coming late, will you? This set and this set, when I heard this thing for the first time when I was in Colombo University, to me it was very confusing. How on earth they can be the same? Because
One is subset of the other one.
yeah, this is a very proper subset. Very proper subset of that. So I couldn't sort of comprehend that they have the same number of elements. So when you are going from finite sets to infinite sets, it makes a big difference. So that's why sometimes people say maths people are weird. In a sense, weird, no? How can you say the same? Actually, number of elements is here is almost twice of the number of elements here, no? You can say so. Anyway, so now let's say here, one way to define this is to say that the two sets have the same size if they have the same number of elements, but we run into problems when it is infinite. Is said the right way to define the concept of two sets having the same size is not immediately obvious, but can be worked out with some thought. One intuitive reason why the sets 1, 2, 3, 4, 5 have the same size is the one can match the elements of the first set with the elements in the second set in the one-to-one correspondence. This one-to-one correspondence is a big thing. I would say, since you are not working on difficult problems, try to do this one. It will be fun for you. Try to find the one-to-one correspondence. One-to-one correspondence means, you know, some function from here to here. It should be one-to-one. It should be on-to. You can do it. If you want another good problem now, you get these integers, no? 1, 2, 3, 4. Because here so far we are not doing challenging problems. We are, try to justify his introduction to natural numbers, then his introduction to integers. Sooner or later we are coming to introduction to rational numbers, then real numbers. After that only we are going to start analysis. So we are on the way. Try to see whether you can do this thing. Right? You know the meaning of sequence, no? You know? Try to write a sequence for both of you. Not both, I'm sorry. 4 of you should try this thing. Write a sequence. That sequence has 1 at infinitely many places. 2 also in infinitely many places. 3 is in infinitely many places. 4 is in infinitely many places. 1000 also in infinitely many places. You are writing one sequence in which every integer appears infinitely many times. Because what we are doing is, just justifying what his introduction thing is inconsistent, this and that. Not mathematically challenging, no. Of course it is challenging to justify that he is consistent, but doing this problem, this one, and that one will be a good exercise. Understand both, no? Here you are going to find one-to-one and on-to function from R to 0, 1. Over there you are trying to construct a sequence consisting of either 0, 1, 2, 3, 4, or whatever, 1, 2, 3, 4, doesn't matter. However, the important thing is every integer appears infinitely many times in the sequence. It's a good problem because all of you are young, much younger than me anyway. Alright, now let's see what he says. Here you are not challenged by the mathematical difficulty. Here in this, when you are doing the exercises in the book, I also go through each and every exercise. You are challenged that you can reason out. That's the only thing here you are facing. Anyway, indeed, this is how we first learn to count. A set, we correspond the set we are trying to count with another set, such as a set of fingers on your hand. I mean, some people do that, no. They don't know how to count. I know, I came from village. There are people, those who don't know how to count. This many coconuts, like that they say. So without counting, they can tell whether they have the same thing. We will use this intuitive understanding as our rigorous basis for having the same size. Equal cardinality. We say that success x and y have equal cardinality if and only if there exists a bijection f x to y from x to y. Bijection means 1 to 1 and on to. So the very important one thing, whenever, this is actual definition. Some definitions are his definitions, no? So they are not going to last forever, because when you are going to study analysis, I guess you have to, for instance, forget n++. You need to refer to other books. No, they don't have n++. That's n+1. But this definition is throughout the world. So that's what I said here also, bijection. No? And once I gave a talk. Can mathematicians count? It was advertised in Daily News and Sunday Observer. Lecture was held at SLAS. You have heard SLAS? Science People Center, that's center. So in newspaper advertisement, can mathematicians count? Lecture delivered by Dr. or Professor W. Ramasinghe, visiting Sri Lanka, blah, blah, blah. Like that, many people came, they were wondering, why on earth can mathematicians count? What do you think? Can they count?
Depends on how you define count.
Anyway, what the reason is that I gave that thing. This is the reason. My whole talk. Now, how you count? I was saying that although coconuts are, you can count coconuts, no, 1, 2, 3, 4, etc. You cannot count heaps of coconuts. You cannot. In other words, the set of all subsets of n and number of real numbers, they are the same. I mean, same. You cannot count real numbers. You can count integers or prime numbers or even integers or integers, but not real numbers. You cannot count. That again, I guess we have to prove, but intuitively we know. So my proof was that, and I used coconuts, trains, and etc. R. Premadasa was the president at that time, so he has sent his staff to the lecture. So R. Premadasa somehow used to like me. I have met with him only once. I was scared of him. Anyway, he says, Professor Ramasinghe is a down-to-earth person. Because my examples are coconuts. You know, many mathematicians, they don't know about coconuts. Even if they know, they pretend not to know. What are coconuts? Like that. Anyway, the reason is that heaps of coconuts or else groups of coconuts is in one-to-one correspondence with the real numbers. Since real numbers cannot be counted, this also cannot be counted. Mathematicians you can eat something, it is only eat audible, no, otherwise you cannot count. Eat. You can count provided it is countable. Otherwise, just because you are a mathematician, you cannot count uncountable things. Again, in Colombo University, I gave a talk once, Mr. Uncountable. These are very interesting. Somehow we haven't come to the interesting stuff yet. We are, he is introducing things. No? Okay, let's go. I guess I'm taking time to say other things. Cardinality of sets makes sense regardless of whether X is finite or infinite. In fact, we haven't defined what finite means yet. Remark, the fact that two sets have equal cardinality does not prelude of the sets from containing the other. Like here, these two have the same cardinality. One is a proper subset of the other. For instance, if X is the set of natural numbers and Y is the set of even integers, even natural numbers, then the map fx to y defined by fn equals to n is a bijection from x to y. Fn equals to n is 1 to 1 onto all these are correct. So it proves that these two sets have the same cardinality. They are in 1 to 1 correspondence. And so x and y have the same cardinality despite y being a subset of x and seeming intuitively as if it should only have half of the elements of x. So to a man in the street, even integers, this set have half of the integers in the or the natural numbers in the set above, but mathematically they have the same thing. So that's why math people are kind of, I don't know, I shouldn't say weird because I am also a math person. But one day at the Ohio State, I was at the swimming pool one Sri Lankan guy showed me. He was so shocked. Oh, I cannot believe. I asked him why. You mathematicians take showers? They think that people don't take showers. Because the reason is that many people find it extremely difficult to understand. I mean, now for instance, after coming here, now you have here more than 1 month. Even now the things you know, you say number of elements in these two sets are the same. People may think, oh, it's a joke. So don't tell these kind of things with others. Anyway, let's say the proposition like x, y, b sets, then x has equal cardinality with x. That is true, no? It's obvious. You can identity map fx equals x. 1 to 1, on 2. Number of elements in x is the same number anyway. If x has equal cardinality with y, then y has equal cardinality with x. It's again an exercise, but it is very easy to prove. If x has equal cardinality with y, that means there is a bijection f from x to y. Then f inverse is a bijection from y to x. So that's the proof actually. Then y has the equal cardinality with x. F inverse is a bijection from y to x. If x has cardinality with y and y has equal cardinality with z, then x has equal cardinality with z. Again, if x has a cardinality with y, then you have f, a bijection. If y has equal cardinality with z, you have g, bijection from y to z. Then g circle f is a bijection from x to z. So that is the proof. So I should not talk about the solutions of the problems, no? Because even if you cannot solve, you don't worry. You should try only. That's the important thing. By trying, you learn a lot. Because these are not any big maths problems, no? This is foundations, basics. So I went very fast. Now this one, no? Let n be a natural number. We want to say that the set x has n elements. Certainly we want to say the set, consisting 1, 2 up to n have n elements. This is true even when n is equal to 0. Then he is going from 1 less than or equal to 0. That is the empty set. That is only rigorous thing. Using our notion of equal cardinality, we thus define, let n be a natural number. A set x is said to have cardinality n if and only if it has the equal cardinality with this set. We also say that x has n elements if and only if it has the cardinality n. Cardinality n means you have a one-to-one onto map from the set you are talking to, the set consisting 1 to up to n. That's all. When we say it has n elements, the same thing, cardinality n, n elements, same thing, and 1 to 1 onto bijection. One can use the set, this set also, set I less than n, instead of 1 to up to n, then over there it begins from 0, no? Set of all I such that I less than n is the set 0, 1, 2, 3, 4 up to n minus 1. Again it has n elements. Why? What is the bijection? Then bijection is also very clear. Because if you want, you can define fi is equal to I minus 1. It is 1 to 1 on 2. Even for little things, you write a one word proof, one line proof, because you may, otherwise you may take a lot of time to write, but you have to make sure you don't overlook anything, because you are studying the foundation. See. Example 367, let ABCD be distinct objects. Then ABCD has the same cardinality as 0, 1, 2, 3, or 1, 2, 3, 4, and thus has cardinality 4. You know, they are trivial. 3. There might be one problem with this definition. A set might have two different cardinalities, but this is not possible. Uniqueness. If a set has, let x be a set with some cardinality n, then x cannot have any other cardinality, that is, x cannot have cardinality m for any m not equal to n. Again here he is proving before you prove even before you prove it, you need to understand given a set, cardinality is unique. This proving is killing the details of the proof, this and that. Here he is proving, suppose n greater than or equal to 1, and by the way, sometimes you may wonder what is the meaning of lemma, proposition, theorem, corollary, this and all of them are actually theorems, or everything is a proof, but lemma is a theorem which uses to prove a little bit bigger theorem. Corollary is a theorem, follows from the theorem or proposition you proved. Proposition and theorem are different. Proposition is also a theorem. Theorem is of course a theorem. No. Proposition is not that, Pythagorean theorem, Pythagoras prameya. No. It's world famous. I mean, there are other theorems in geometry that we don't talk about. So, proposition is that kind of thing. It's less important. But less important doesn't imply that it is not important. But one way of, I say, suppose n greater than or equal to 1 and x has cardinality n, then x is non-empty. And if x is any element of x, then the set capital X minus singleton x, that is x with the element little x removed, has cardinality n minus 1. The funny thing is here, so far we don't know what is the meaning of n minus 1. No, we haven't defined it. We know only class. That's the thing, I mean, this book, sometimes we have to use the knowledge from other sources to understand this book. So, but many other books are not this way. They construct from it's like a ladder. You go to the first rung, second rung, third rung, like that. Here he is using even axiom of choice. You just did A-level like his last year also, today axiom of choice. He hasn't talking about even, this one is not done still. Anyway, cardinality n minus 1 mean, the n minus 1 we know of. I guess this proof is not that difficult, so I think you can go through it, no? Is it? So shall I go it? Not really. No need, no? This is, it's a matter of reading it. But you should read carefully. That's the important thing. Thus, for instance, we now know, thanks to proposition 3.6.4 and 3.6.8, that the sets 0, 1, 2 and 3, 4 do not have equal cardinality, since the first set has cardinality 3 and the second set has cardinality 2. Now, from this thing we know that they are different. He is talking about finite sets. A set is finite if and only if it has cardinality n for some natural number n, and a natural number includes 0 also. Otherwise, the set is called infinite. If it is not finite, it is infinite. This is true for sets, but if a set is not open, you cannot say it is closed. You know open sets? So, say an interval, if the interval is not open, you cannot say it is a closed interval. It's not true. But here, if the set is not finite, then it is infinite. If that's definition, by the way, if x is a finite set, we use that thing in x to denote the cardinality of x. So, very important thing, I guess to this day you said, strictly speaking, n minus 1 has not yet been defined in this text. For the purpose of this lemma, we define n minus 1 to be the unique natural number m, such that m plus plus equals to n. He has a definition for that also. Anyway, this m is given by lemma 2.2.8. Anyway, doesn't matter. So far, you said if a set has, say, 4 elements, you counted, no? You say some thing, there are, if you want to say 3 books, you count 3 with the 1, 2, and this again with this one 3. Here is not the way you are defining a map from 1 to set consisting 1, 2, 3, 4 up to n to the set a bijection. That's how we prove the number of elements for cardinality. So you need to get used to this thing. Here he is talking the set 0, 1, 2 and 3, 4 are finite as the empty set 0 natural number. Number of elements in 0, 1, 2 is 3 and this is given. Now we give an example of an infinite set. The set of natural numbers n is infinite. Let's read that proof because first time we are going to prove something is infinite. Suppose for sake of consideration that the set of natural numbers n was finite. So it had some cardinality, number n is equal to n, number of elements in the set capital N is equal to n. Then there is a bijection f from 1, 2, 3, 4 up to n to n. One can show that the sequence f1, f2, fn is bounded. Again, bounded. You don't know the meaning of bounded. That's why I say. Or more precisely, that there exists a natural number capital M such that fi less than or equal to m for all I between 1 and n. That is the meaning of bounded anyway. But the natural number m plus 1 here, but in maths, when you say a bounded, that capital M does not have to be a natural number. It can be a real number. If you take 1, 2, 3, 4 is bounded by 5.1. The meaning is fi less than or equal to m. It's not necessarily, m doesn't have to be a natural number, but anyway, but then he says m plus 1 is not equal to any of the fi, contradicting the hypothesis that f is a bijection. So here he used the fact that this set is bounded, and before that we haven't seen even the word bounded. Does not matter. Anyway, so the proof. This is the proof anyway. Capital N, set of all natural numbers, is not finite. If you assume it is finite, definitely it is bounded. You can use that bound to be, for instance, a natural number. Then that number plus 1. Then here he wrote plus 1, not m plus plus. So I don't know when you use m plus plus, when you are going to m plus 1. That kind of a question. Anyway, this is the proof. If somebody asks you to prove that capital N is infinite, according to this book, that is the proof. One can also use similar arguments to show that any unbounded set is infinite. For instance, the set of the rationals Q and the reals R, we will construct in later chapters, are infinite. However, it is not possible for some sets to be more infinite. It is possible for some sets to be more infinite than the others. Here R is more infinite than this one. These things we will be proving. Right now what is happening is he is not willing to assume you know anything. So that's why he is defining natural numbers. He defined using piano axioms, 5 of them, which included principle of mathematical induction. Now so far he has not defined integers, negative integers, he hasn't done, but he came to cardinality. It is a good one anyway. This try to, you can prove this, no problem. Like if a set has then the number of, here X is a finite set, then simple X is another object. The number of elements in X union X is equal to number of elements X plus 1. The X and Y be finite sets, then X union Y is finite. and number of elements in X union Y less than or equal to number of elements in X plus number of elements in Y. I mean, this is intuitive. In addition, X and Y are, if in addition X and Y are disjoint, that is meaning is X intersection Y is empty, then number of elements in X union Y is the number of elements in X plus the number of elements in Y. That is again trivial. Let X be a finite set and Y be a subset of X, then Y is finite. That is an important result. Every subset of a finite set is finite. But every subset of an infinite set is, you cannot say infinite. So this is C is characteristic for finite sets. Let X be a finite set and let Y be a subset of X, then Y is finite. And number of elements in Y less than or equal to number of elements in X. By the way, this notation number and Y used for finite sets you have to keep in mind. If in addition Y is not equal to X, that is Y is a proper subset of X, then we have number of elements in Y strictly less than number of elements in X. Again, he says if X is a, these are easy to prove, not difficult. You have to make your hands dirty. Try to prove. If X is a finite set and F is a function, then Fx is a finite set. Again, it is a, I mean, it's an intuitive thing. Image of a finite set is again finite. Fx is a finite set and number of elements in f of x is less than or equal to number of elements in x. If in addition f is 1 to 1, then both of them are the same. That is also clear. Let x and y be finite sets. The Cartesian product x cross y is finite and number of elements in x cross y. When you are proving these things, by the way, this is quite a lot of writing. If you are going to write details, just write the bijection. No, that's enough. Let x and y be finite sets, then y to the x defined in axiom 3.10 is finite. Can we see the reason to write number of elements in y to the x is equal to number of elements in y raised to the power number of elements in x. He discussed about exponentiation, no? 2 to the 3, so over there he said. So, said, may Puta, you were not there. Did you read the book? Y to the x is, this is the set of all functions. F is a function from x to y. F is a function from x to y. We have the notation. At that time we were wondering why he did not use x to the y instead of y to the x. This is the reason. Number of elements in y to the x is number of elements in y raised to the power number of elements in x. Again, it's not difficult to prove. See, it's an easy exercise. Proposition 3.4 suggests that there is another way to define the arithmetic operations of natural numbers, not defined recursively as, but instead of using the notion of union Cartesian product. You don't need that. That's not. This concludes our discussion of finite sets. We shall discuss infinite sets in chapter 8 once we have constructed a few more examples of infinite sets such as the integers, rationals and reals. Did you get any challenging problems in homework? I did not notice.
You keep it till I'm going to do it today, that's it.
Because in real analysis, I mean, when I gave this problem to Colombo University students, write a sequence consisting of only integers, but every integer appears infinitely many times, they couldn't believe there is such a sequence. But it's a very simple answer. Can you tell me now? A sequence, it has 1, 2, 3, 4 integers, but in the sequence, 1 appears infinitely many times, 2 infinitely many times, 3 infinitely many times, like that. Can you think of a sequence? It's a good problem. Because you don't have that kind of problems in this homework, but here, when you are doing homework, you have to find the correct proposition, lemma, this and that to answer. Then now here let A and B be set so that A cross B and B cross A have equal cardinality by constructing an explicit bijection from the two sets, between the two sets. I mean, that is very easy. But the question I asked is not that easy. Again, this A to the B, raised to the power C is A to the B, C. Construction, lot of work, however, if you are going to write. And pigeonhole principle. You have pigeonhole principle is actually like, you know, these pigeonholes in the sense that mailboxes in post office, some post offices you have some holes in which, I mean, say you four of you, so your letters, when they receive the letters to your address, they put to your pigeonhole, your letters to your pigeonhole, so 4 of them, no. If there are, pigeonhole principle is, if there are 5 letters, at least one person must have received 2 letters. 4 people, 5 letters, at least one of you should have received 2 letters. That is called pigeonhole principle. This pigeonhole principle is very famous, but it's not a difficult thing. It's clear, no? If you have, for instance, pigeonhole principle, say 4 plates. Oh, my plates. You don't learn how to draw a plate from me. say cups or something, you put any name you wish. And suppose you got 5 waddies. If you want to put waddies to these cups, since there are 1, 2, 3, 4 cups here, you have to put 2 waddies to at least 1 cup. That is called the pigeonhole principle. In sports, in +1 objects, then one place must get at least 2. That is called pigeonhole principle. Yeah. Pigeonhole principle has different ways of saying. Now you can do this problem. Can you see the proof? Tell me now. It says, can you see number union of A1 up to AN is finite. All are finite sets. Number of elements in the whole union is strictly greater than N. Whole union. You are not told that whether they are disjoint or so, nothing like that. You have A1 union, A2 union, A3 union, AN. That's the meaning of that, no? The number of elements in this A1 union, A2 union, A3 union is strictly greater than N. So that there exists one I belongs to 1 to up to N such that number of elements in the set AI greater than or equal to 2. Can you do it now? You must be able to. I will give you 2 minutes, otherwise I am not going to do it. It's very simple. You here, to this day, you haven't got very, I mean, you guys are right, no? Very challenging problems. Kind of logical thinking problems you got. This is one of them. And other things you have to match up his axioms, this and that, applications of that. Not very difficult. This is a question you can do. Pigeo in spelling, correct? When I'm wearing glasses for you, I cannot see sometimes.
Using proof by contradiction, no?
Okay.
You can do it by using proof by contradiction, no?
Mm-hmm.
So first of all, suppose for all I belongs to 1 to n, such that
No,
number-
such that, no, you don't
Yeah,
say such that.
yeah.
Haven't studied.
Yeah. For all I within 1 to n, number of elements in AI is less than 2. So if you all add the all AI, the number of elements in AI from 1 to n, you get the union I 1 to n AI is less than n. So that's a contradiction. Is that equal? Is not equal. I think that. Yeah, this some
Can you do it? He said something, but is this correct? But
it's not complete.
eh?
It's not complete what I said.
Can you say?
Is less than or equal to n.
So, what is the first line proof? I will write. I should not do it, this is homework, but doesn't matter.
Yeah.
Because this exercise, since it is purely, logical thing, then he said,
So suppose
we are saying, suppose,
A1 to A we find as yet such that given statement number union of AI, the elements of union of AI is greater than n.
hmm,
Now assume for all I belongs to 1 to n, the elements of AI is strictly less than 2. Since the number of elements in AI must be greater than or equal to 2, since number of elements in AI must always be greater than or equal to 0, we can show that the number of elements in AI is strictly less than 2 means number of elements in AI is strictly less than, is less than or equal to 1.
that line is correct.
Yeah. Now add it up sigma I equals 1 to n on both sides.
Because you have wrote that, yeah. Yeah, it is it. So I have to go this way, no? You wrote it, no? I We proved number of elements in, is that result, number of elements in A union B less than or equal to number of elements in A plus number of elements in B. Is it a proper result or is it this kind of problem? I cannot remember that. Proposition. If it is a proposition, we can use it. Here, finally show that A union A. Anyway, we know that, no? We know that.
In the propositions, sir. In the propositions.
In the propositions, there was a proposition who? There was a proposition, number of elements in who? A union B is less than or equal to number of elements in A plus number of elements in B. This was a proposition, no? So we can prove, using induction, we can prove that the number of elements in A1 union A2 union bingo bingo bingo. This is induction problem. Less than or equal to number of elements in A1 plus and so on plus number of elements in A. This is a result. Then using the principle of mathematical induction, next result can be proved. From that, then you get this is less than or equal to number of elements in A1 plus number of elements in A2 plus and bingo 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 plus number of elements in AN. Then all of them are less than or equal to 1. So this 1 plus 1 plus bingo bingo plus N, which is equal to N, is a contradiction. It is a contradiction. So anyway, now that problem is done. Right? Buddha? All right. So pigeonhole principle is also done. Now what? What is next? But nothing comes now. Go. Coming. Integers and rationals who went past. You know, funny thing, I was head of the Department of Mathematics at Computer Science of the Open University of Sri Lanka for a bunch of years after when I came from USA. Then over there in USA, I used the computer to use calculus. As a result, in my office, I was provided with 2 computers, and of course, computer lab has many computers. Then in Colombo University, when I was the head, I was given again 2 computers. But I don't know how to use a computer. Even today, somebody may think, oh, Dr. Ramasinghe, he was the head of the Department of Mathematics and Computer Science, so he must be knowing about computers. Actually, I am the first person who introduced a computer lab to Colombo University. I am the person, historical thing. Because before that, students were taught only the things he likes: relativity, quantum mechanics, analytical mechanics. This sort of thing, theoretical physics things were taught. But students could not get jobs for this. No? Then I am the one who introduced applied mathematics, computers, this and that. Anyway, the thing I wanted to tell was that I did all that, but I don't know you. Here, let's read it. Integers and rationals. I guess we are going slow. No, what to do? I cannot help it.
We ended 3 chapters, right?
Eh?
We ended 3 chapters, right?
Oh, we finished 3 chapters. Not bad in a sense. Let's see whether, how about,
So
huh?
we have the interval now. It's 52.
Yeah, okay. Let's have it.